Welcome back to the course entitled Elementary Electrochemistry. In the previous lecture, we have discussed about the determination of conductance, specific conductance and equivalent conductance. And if you remember, I had given you a simple problem to work out, which is this one. So as I said, we need the value of the specific conductance of 0.1 normal KCl solution at 18 degrees centigrade, which we can take from the table as 1.1192 into 10 to the power minus 2 mole centimeter inverse. And what we know is that cell constant, that is K, is equal to L by A is equal to L KCl into the corresponding resistance R, and R has unit ohm, L has unit mho or ohm inverse, second inverse. So this K will have unit centimeter inverse, and the specific conductance of NaCl, that is L NaCl, is equal to L by A into R, or equal to L KCl into small r by capital R. Right? That small r is the resistance of the solution of KCl, and capital R is the resistance of NaCl. So one can calculate the equivalent conductance, that is lambda, for 0.05 normal NaCl using the following equation, that is lambda equal to 1000 by C into L NaCl, which is then equal to 1000 by C into L KCl into small r by capital R. So then one can easily put the values 1000 by 0.05 centimeter to the power minus 3 per cubic centimeter into 1.1192 into 10 to the power minus 2 mho centimeter inverse into 86.8 ohm divided by 203 ohm. So this gets cancelled, and from this centimeter to the power minus 3 and centimeter inverse, we have centimeter square. So the value turns out to be 95.17 mho centimeter square. So what we get is that the unit of equivalent conductance is mho centimeter square, right? So these things you should remember, that the units of conductance, specific conductance and equivalent conductance are not same, because they have different physical significance, physical meaning. As a result, their units are also different. So now in this class we will start discussing about the the variation of equivalent conductance, that is lambda with concentration. See, one can calculate the values of lambda of KCl using the values of L of KCl for different concentration of KCl in water. So if you do that, if you remember that we had given you a table for 3 different concentrations and we had 3 different values of L. So from that one can calculate the value of lambda. I leave that calculation to you. You see that there is a difference, there is a significant change in lambda. What is observed? It is observed that with with dilution, lambda increases and reaches a limiting value at infinite dilution. And this behavior is not same for strong and weak electrolytes. For strong electrolytes, like HCl, KCl, NaCl, etc., the plot of lambda versus square root of concentration is nearly linear, with increasing values of lambda for decrease in concentration, that is decrease in the value of C. So what is observed? The experimental values, if you try to plot the values of lambda for different electrolytes with square root of C, we see that for HCl the straight line is like this, for KCl it is like that, some lanthanum chloride it is like this. So now when we try to extrapolate this to a concentration C equal to 0, it reaches a value. So the value at C equal to 0 is denoted as lambda 0. So this lambda 0 is the extrapolated equivalent conductance of a particular salt solution at infinite dilution. Lambda 0 is the equivalent conductance of an electrolyte at infinite dilution. So when you see this kind of plot, it looks like it is following a straight line, which is lambda c equal to lambda 0 minus some concentration, some constant b square root of c. This is called the equivalent conductance at infinite dilution. Right? Now, what we know is the conductance of a solution depends on the concentration of the electrolytes and the speed, that is the nature of the ions present. So when we start thinking about it, what we see is that in case of weak electrolytes like acetic acid, the graph or the plot changes significantly. For weak electrolytes, we see a graph like that, which tends to go up in this manner. So when you try to extrapolate it to the concentration C equal to 0, it reaches again some value lambda 0. So that is the lambda 0 of, say, acetic acid. So it is very clear that when we have strong electrolyte, the behavior of equivalent conductance is nearly a straight line with respect to change in concentration, whereas when you have a strong weak electrolyte like acetic acid, then the nature of the plot changes. So this dilution experiment we will be demonstrating during the experimental section. So for that, I will just explain what experiment we will be doing during this experimental session. So we will be taking two types of solutions, HCl and acetic acid. We will take one normal HCl solution and one normal acetic acid solution in two volumetric flasks, and using a very standard burette, 50 ml burette, we will prepare exactly half dilute, that is N by 2 solution. Then from that, again by half dilution, we will prepare N by 4 solution. From that, we will prepare N by 8. From that, we will prepare N by 16. From that, we will have N by 32. And then again N by 64. And then if somebody wants to continue, can go down to 1 by 128, and then 1 by n by 256. This depends on how many solutions you want to measure. But what happens is, for very, very dilute solutions, the resistance increases significantly, and then the measurement of resistance using the standard device becomes difficult. So we may not be able to determine the conductance of these solutions during the experiment, which I have to do and then to demonstrate. We will see what happens. I am just explaining what the experiments we are planning. So like that, you will do n by 2 acetic acid way down to n by 64 acetic acid solution. So what we will measure in these two cases, two different sets of solutions, we will measure the conductance lambda for all the solutions, and we will be using a conductivity cell of cell constant equal to 1 centimeter inverse, right? So that whatever conductance we measure is directly converted to specific conductance L, and from those L's, using the value of the concentration of the solutions, we will calculate the values of lambda C, right? Lambda C is nothing but 1000 L by C. So using this expression, what we will have is a table of lambda C versus C, which then can be converted to square root of C. So we will have values of lambda C for one normal solution to a lowest value, and we will have this for both HCl and acetic acid. And then we will try to plot those values of the equivalent conductance versus square root of C, and we will verify the plot which we have drawn in the previous slide, that is lambda versus square root of concentration. This experiment is called the validation of Oswald dilution law, and this is one of the very important experiments in electrochemistry to determine the nature or behavior of strong and weak electrolytes. So by doing this experiment, one can identify whether one electrolyte should be considered as a strong electrolyte or it has to be considered as one of the weak electrolytes. Now I will just introduce you to the another aspect of these ion conductivities, which is named after Kohlrausch. Kohlrausch's law of independent migration of ions. It was observed that the lambda 0 for HCl, lambda zeros for HCl, KCl, NaCl, KNO3, NaNO3, etc. follow follow a trend. What is the trend? The trend is the difference between the lambda 0 values of different salts with same anion were same. That is lambda 0 KCl minus lambda 0 NaCl is equal to lambda 0 KNO3 minus lambda 0 NaNO3 equal to lambda 0 KBr minus lambda 0 NABr. So, from this observation, Kohlrausch proposed that when we write lambda 0 NaCl, we are actually meaning that there is some L0 Na plus and L0 for Cl minus. That is, these are called the ionic conductances or simply ion conductances at infinite dilution, and the values are constant. That means lambda 0 KCl can be written as L0 K plus L0 Cl minus. So when you do the subtraction lambda 0 KCl minus lambda 0 NaCl, it simply turns out that you are doing a subtraction of L0 of K plus to L0 of Na plus, right? So from this, what was proposed is that the equivalent conductance at infinite dilution is equal to the sum of the ion conductances at infinite dilution, right? So now the values of L0 cation and the value of L0 anion are determined from their transport numbers, that is T plus and T minus. So what is the value of L0 cation? It is nothing but some constant K1 into the number of cations, that is N plus, into the charge of the cation, that is Z plus, E into U, the speed of cation. Similarly, L0 anion is another constant K2 into N minus, Z minus, E into V. Now, for electroneutrality of the solution, the product K1 N plus Z plus E should be equal to K2 N minus Z minus E. So when we try to calculate the value of lambda 0, which is nothing but L0 cation plus L0 anion, we can do this by doing K1 N plus Z plus E into U plus, again instead of K2 N minus Z minus E, we write K1 N plus Z plus E into V, which is equal to a constant. Suppose this quantity is a constant K into U plus V. So lambda 0 is K into U plus V. So now if I try to do a simple math, that is the ratio of L0 cation by lambda 0, I think we should write lambda 0 as subscript 0 equal to lambda 0 cation is this quantity, which is K into U divided by K into U plus V, which is equal to U by U plus V. And from our earlier knowledge of transport number, U by U plus V is nothing but the transport number of cation. Therefore, L0C is nothing but transport number of cation multiplied by lambda 0 of that particular electrolyte. Similarly, L0 anion is equal to the transport number multiplied by lambda 0, T minus. Because you see, T minus is equal to 1 minus T plus, that is 1 minus U by U plus V, that is equal to V by U plus V, which is then simply equal to L0 anion by lambda 0. So we can use these equations for determination of ion conductances for different electrolytic solutions. So using this concept, one can easily determine the value of equivalent conductance at infinite dilution for any other electrolyte which are not known or new, or maybe one of the weak electrolytes. So for example, if you want to determine the equivalent conductance at infinite dilution for acetic acid, which is CH3COOH, in terms of ion conductances, one can write it as L0 of H plus L0 of acetate anion. So now the values of L0 for H plus and OAC minus can be rearranged like this: L0 of H plus L0 of Cl minus plus L0 of Na plus L0 of OAC minus L0 of Na plus and L0 of Cl minus. Right? So you see, we have added L0 for Cl minus, subtracted that. We have added L0 for Na plus and subtracted that, and this equation remains the same. So this first term is nothing but lambda 0 for HCl plus the second term is lambda 0 for sodium acetate, and the third term is lambda 0 of NaCl. So, if one determines the equivalent conductance at infinite dilution for these three strong electrolytes, HCl, sodium acetate and sodium chloride, then by doing a simple mathematics, addition and subtraction of these three quantities, one can easily calculate the value of lambda 0 for acetic acid. So, using this law of ion conductivities or the Kohlrausch's law of ion conductances, one can easily determine or calculate the equivalent conductance at infinite dilution for any electrolyte, for example, acetic acid, formic acid or any other weak electrolytes. So, we will end this lecture here and we will start from here in the next class. Thank you.